Hello everyone, and thank you for joining our session on reverberation chambers and their growing demand in automotive component testing. In this talk, we will present briefly long-established and universally accepted EMC measurement sites that most of you are already accustomed with, and then we will follow our presentation with the introduction of a relatively new test facility, namely the Reverberation Chamber. We will present its operating principle, various steering techniques, and then we will finish with a particular reverberation chamber solution focusing on automotive component testing. The first well-established EMC test facility is the open area test site. The open area test site is basically a flat piece of land which is free of physical obstacles, RF surrounding signals, and equipped with a metallic ground plane. The use of such a highly reflective floor more closely mimics a real-life scenario by introducing and accounting a reflective wave from the Earth. Since nowadays it is very difficult to find a location not polluted by external noise signals, the semi-anechoic chamber is a fitting alternative. Such test facility consists of an RF shielded enclosure which ensures cancellation of false signals from the outside world, and RF absorbing material on the inside, which dampen all unwanted reflections coming from its walls and ceiling. In contrast to the semi-anechoic chamber, the fully anechoic room aims to absorb energy in all directions. To accomplish this, the FAR concept implies the utilization of absorbing materials upon all chamber surfaces, including its floors. So, what if we could level up? A relatively new method that is becoming more and more popular and acknowledged in the recent years relies on the use of reverberation chambers. We could say that the operating principle of reverberation chambers is the complete opposite of anechoic chambers. Instead of keeping wall reflections under control, thanks to RF absorbers, the reverberation chamber has in turn highly reflective walls in order to have as much reflections as possible, offering the so-called multipath scenario. Its basic principles are electromagnetic resonance and mode steering. When energy is injected inside the cavity, we end up with a 3D standing wave pattern, with areas of high fields, commonly referred as peaks, and areas of low fields, commonly referred as valleys. If we introduced a highly reflective steerer in this cavity, then by changing the position of the steerer, we will vary the electromagnetic boundary conditions of the chamber, resulting in different standing waves. By taking a sufficient number of steerer positions and superimposing the resulting electric fields, we end up with a statistically uniform, isotropic, and randomly polarized electric field. In other words, the reverberation chamber is a cavity resonator with a steerer. Here, I would like to stress out that the electric field inside the reverberation chamber is not uniform for a specific position of the steerer. Again, it has peaks and valleys, meaning that for every steerer position, two various points inside the chamber shall experience very different electric fields. But by moving the steerer, we are able to alter and shift these peaks and valleys, making sure that every point inside the predefined test volume experiences statistically similar fields. Just to give you an example, I will share with you the results from an actual experiment inside the reverberation chamber. In this simple experiment, we measured the electric field strength from two different points inside the reverberation chamber for one steerer revolution. In the y-axis, you can see the total electric field strength, while in the x-axis is the steerer position in degrees. As you can expect, the measurements from the considered 2 points are not following the same trend and appear to be totally random. For example, when the steerer is at 60 degrees, the measured field at point A is at a peak and equal to 135 volts per meter, while for point B is only 75 volts per meter. On the other hand, at 158 degrees, the received power at point A is 77 volts per meter, while for point B is at a peak and equal to 125 volts per meter. Nonetheless, when we look at their statistical properties, such as the maximum, minimum, average value, and standard deviation, we will find out that they are almost identical. Here comes the number one advantage of reverberation chambers. In anechoic chambers, the AUT is merely illuminated by a direct wave coming from a transmit antenna during radiated immunity. On the other hand, in reverberation chambers, the AUT is exposed from all sides and directions, thanks to the rich multipath environment formed. Thus, the weak spots of the AUT will be surely exposed and highlighted during reverberation chamber testing, and that is why we say that there is no room to hide EMC problems in a reverberation chamber. Aside from that, there are more advantages of the reverberation chamber method. Statistically uniform field, its ability to generate high electric fields with moderate input power due to its highly reflective walls, high test reproducibility and repeatability, ability to house and test large AUTs, and last but not least, the reverberation chamber is a better representation of real-life environments, thanks to its nature of illuminating the AUT from various angles, polarizations, and orientations. Of course, every test method has its limitation, and reverberation chamber is no exception. The most notable one is its low frequency bound, which can be approximately as low as 50 to 80 MHz for a big chamber. The limitation occurs because the resonant frequencies of the chamber depend on its physical dimensions, meaning that for testing at low frequencies, such as 10 MHz, the size of the reverberation chamber should become impractically large. Another limitation is that the magnitudes of interest are defined statistically. Moreover, due to the random generated fields inside the reverberation chamber, all information regarding the orientation and polarization of a signal that may cause the test to fail are lost. But how can we steer the field in a reverberation chamber to achieve a statistically uniform field? Multiple steering methods have been proposed and tested throughout the years. However, all of them can be divided into two main groups. Mechanical mode steering, where an electrically large and highly conductive object is moving inside the chamber, and electronic mode steering, where the time-changing boundary conditions are achieved by electronic means, like the use of multiple antennas and/or varying their phases. Since EMC test standards solely accept the mechanical mode steering methods, hereafter we will focus on such techniques and present four concepts. The first and most common steering method is through employing a rotating Z-fold steerer. To provide a good chamber performance, the Z-fold steerer should have an asymmetrical shape, such that a non-repetitive field pattern can be obtained over one revolution of the steerer. Another steerer design is the oscillating wall steerer. This steerer is designed to act as a moving scatterer, but instead of rotating, it is oscillating back and forth, acting as a moving quasi-wall inside the chamber. One of the main advantages of the oscillating wall steerer is the increased working to total volume ratio compared to the traditional Z4 steerers, thanks to more efficient occupation of the space within the cavity. This is especially evident in large chambers, where big equipment under test need to be measured, for example, large vehicles. Another approach for achieving field uniformity is by shaking rapidly a tent with irregularly shaped walls made of flexible conductive material. This is known as the vibrating intrinsic reverberation chamber. The most peculiar one is the stadium chamber, which consists of two hemispheres with irregularly shaped caps connected by a cylindrical section. In this example, the bottom cap provides the steering by rotating using a belt drive mechanism. Then, there is a subsequent question raised. How can we quantifiably assess the ability of a stirrer to provide a statistically uniform field inside the chamber? For that reason, international standards have come up with a field uniformity validation procedure in order to characterize a reverberation chamber. In brief, it demands that the standard deviation of the electric field measured at the 8 corners of the working volume per 1 stirrer revolution should be lower than a standard defined limit. After the validation procedure is successfully completed, the reverberation chamber can be used for various tests such as radiated immunity, radiated emissions, and antenna efficiency. Due to its advantages, various test standards accept and encourage the reverberation chamber test method. The most distinguished ones are the IEC 61000-4-21, which describes in detail RC characterization as well as test procedures for radiated immunity, radiated emissions, antenna measurements, and a novel method for shielding effectiveness evaluation. Military standards such as MIL Standard 461G and RTCA TO 160G support the reverberation chamber method for radiated immunity testing. ETSI and CTIA standards recognize the reverberation chamber for total radiated power and total isotropic sensitivity. Last but not least, ISO 11452-11, used for automotive component testing, as well as the upcoming ISO 11451-5, aimed at vehicle measurements, encourage the use of reverberation chambers for radiated immunity testing. We must highlight here that in all the standards mentioned above, the reverberation chamber is regarded as an alternative test method to the well-established anechoic chamber. But recent technological innovation has eventually urged reverberation chambers to challenge the status quo. This shift was initiated by the automotive industry. The transition from mechanical to all digital electronic instrumentation, fully electric cars, autonomous driving technologies, and numerous advanced features such as pedestrian detection, parking and lane assist, adaptive cruise control, network connectivity, and satellite navigation have pushed big automotive manufacturers to steer towards more excessive and harsh EMC test methods in order to ensure the firm and reliable operation of the vehicle's electronic components, and thus the functional safety of the vehicle. That is why the radiated immunity testing using a reverberation chamber has recently become a compulsory validation method of automotive components for some of the biggest automotive manufacturers, such as the PSA Group. Moreover, it is considered the preferred test method by Ford and General Motors. This fact motivates us to look deeper and concept a reverberation chamber for radiated immunity automotive component testing following the standard directives. In this use case, the chamber validation should be according to ISO 11452-11, which describes the radiated immunity test procedure for automotive components. The chamber operating frequency range will be set from 200 MHz to 6 GHz, and the test table used for placing the EUT as well as the auxiliary equipment will be sized as 2.5 by 1 meter. In the next slides, we will share with you the most crucial design criteria for concepting the chamber. According to ISO 11452-11, the working volume should be of a sufficient size to house the EUT. The distance of the working volume from every chamber surface, antenna, and stirrer shall be at least a quarter of a wavelength of the lowest usable frequency, in our case 200 MHz, and that the EUT, test bench, and support equipment should not occupy more than 8% of the total chamber volume. The chamber size shall be large enough to have sufficient number of resonant modes at the lowest usable frequency. Having more than 100 is considered a good practice. The stirrer shall have an asymmetrical, non-repetitive shape with dimensions as large as possible with respect to the chamber size and working volume. Finally, the antennas used shall be linearly polarized with more than 75% efficiency. They shall be placed in non-conductive stands with a quarter of a wavelength separation from any surface. Finally, the transmit antennas shall not directly illuminate the working volume. After taking all these parameters into account, we come up with a concept design as you can see in the slide. The dimensions of the resulting chamber are approximately 5 by 4 by 3 meters. As you may also notice, the working volume is set to accommodate both the wanted test table as well as the receive antennas. Now we can test the radiated immunity of an automotive component and ensure its stable performance under harsh electromagnetic environments. To sum up, reverberation chambers create a more realistic test environment that is able to reveal more potential EMC problems, leading to more reliable and higher quality electronics. It can be used for a variety of tests, from radiated immunity and emissions to antenna efficiency and shielding effectiveness. It is now deemed compulsory for automotive components from many automotive manufacturers, and the chamber design can be tailor-made in order to support specific test requests. Before ending this presentation, I would like to take the opportunity to inform you that Comtest has broad experience in designing and building EMC test chambers since 1985. We have been building reverberation chambers since 2008, and ever since we have delivered more than 30 reverbs worldwide. Moreover, the innovative oscillating wall stirrer is invented by Comtest R&D department and is a patent in design. At Comtest, we believe that reverberation chambers are the way forward for EMC testing. Thank you.